everyone, and welcome. Today, we are going to pull back the curtain on the world of IP addressing, and we're zeroing in on a really important category, Class B. Trust me, by the end of this, you'll be able to spot one in a heartbeat and know exactly what you're looking at. Okay, so let's just kick things off with a little puzzle. Look at this IP address, 130.2.3.4. Right now, it's probably just a jumble of numbers. But stick with me here, because we are about to decode this thing piece by piece. So the first thing you've got to know is that not all IP addresses are built the same. They're actually sorted into different classes. And the biggest clue to figuring out which class an address belongs to, well, it's hiding in plain sight, right there in that very first number. Now, just a super quick refresher, I promise. An IPv4 address, at its core, is just a long 32-bit number. The only reason we break it up into 4 chunks with dots in between is to make it readable for us humans. Each of those chunks is called an octet, and that's just a fancy word for a group of 8 bits. So where's the magic trick? Well, for a Class B address, the whole classification, everything, it all comes down to the first 2 bits of that entire 32-bit sequence. Think of them as being locked in place. They're like a secret handshake that only Class B addresses know. And that secret handshake, that special binary prefix, it's always 10, always. If you look at the raw binary of an IP address, and it starts with a 1 followed by a 0, boom, you're looking at a Class B address. It's the absolute definitive signature. Okay, so syncing in binary is great if you're a router, but what about the rest of us, right? Let's translate this 10 prefix into a simple range of numbers, something that we can actually spot without doing a bunch of math in our heads. And this is how it works out. If you take that 10 prefix and then you fill the rest with all zeros, you get the number 128. If you do the opposite and fill the rest with all ones, you get the number 191. These are our boundaries. So here it is, the key takeaway. Forget about the binary for a second. This is the simple rule you need to remember. If you see an IP address and that very first number is anything from 128 all the way up to 191, you've found a Class B address. It's that easy. Awesome! So now we know how to spot one, but what does a Class B address actually do? Well, the next step is to understand its blueprint. You see, every IP address is really 2 things in one. One part identifies the whole network, and the other part points to a specific device on that network. Now for Class B, this structure is beautifully simple. It's a perfect 50-50 split. The first 2 numbers, that's 16 bits, define the network. You can think of this part as the city and street name in a mailing address. And the last 2 numbers, the other 16 bits, they define the specific device, or the host. That's your host number. And this chart really drives that point home. It's a perfectly balanced design. Class B dedicates exactly half of its power to identifying the network and the other half to identifying all the individual devices that live on it. So how many of these networks can there even be? Well, remember those first 2 bits are fixed as 10, which leaves us with 14 bits left to play with for the network ID. So if you do the math, 2 to the power 14, that gives us a grand total of 16,384 possible Class B networks. But this is where things get really big. For every single one of those networks, how many devices, how many hosts can we have? For that, we get a full 16 bits. And 2 to the power of 16 is a whopping 65,536. That is a ton of house numbers for every single street. All right, let's put all this theory into practice. It's time to circle back to that mystery IP address from the very beginning and see what we can figure out now that we have all the clues. Here it is again, 130.2.3.4. So first question, what class is it? Well, that first number, 130, falls right in the middle of our 128 to 191 range. So, check. We know for a fact it's a Class B address. Easy. Okay, but what's the next step? We know this is a specific house on the internet, but what city and street does it belong to? To put it in network terms, what's its network ID? Finding the network ID is actually a pretty standard process. You take the IP address, and then you combine it with a special number called a default mask using a bit of logic. This process basically strips away the host part of the address, leaving you with only the network part. And here's what that looks like in action. The default mask for Class B is always 255.255.0.0. When you combine them, the 255s basically say keep this part, so the 130 and the 2 pass right through. The zeros in the mask say discard this part, so the 3 and the 4 get turned into zeros. And that gives us our answer. The city and street, the network that this device lives on, is 130.2.0.0. Every single computer, phone, or printer on this particular network is going to have an address that starts with 130.2. So that means we have 65,536 addresses to hand out to devices, right? Well, not so fast. It turns out 2 of those addresses are special. They're reserved for specific jobs, and you can never assign them to a regular device like your laptop. The very first address in our example, 130.2.0.0, is reserved to identify the network itself. You can think of it as just the name of the street. And the very last address? That's the broadcast address. Sending a message there is like shouting, "Mail for everyone on this street." It goes to every single device. So once we take away those 2 special addresses, we're left with our actual range of usable IPs. For our 130.2 network, the first device you can assign is 130.2.0.1, and the very last one is 130.2.255.254. That leaves us with a grand total of 65,534 usable addresses for our devices. And that massive scale is exactly why Class B was designed in the first place. It was the perfect solution for big organizations, think major universities or huge corporations, that needed tens of thousands of IP addresses for all their computers, all neatly organized under a single network banner. But you can probably see the problem here, right? This system is great for the giants, but it's also unbelievably wasteful. Giving a block of over 65,000 addresses to a company that only needs, say, 100 of them, that's a huge waste of precious IP space. And that very problem, that inefficiency, forced the engineers of the internet to ask a really important question. What comes next?